Hello, I'm Diego. This is OPTI380A lab report number 9, diffraction.
I'm Tyler McKenzie.
And our TA's name is Sidat. So this is the outline of the experiment. The first part is the diffraction apertures, and the second part is measuring laser beam divergence. So,
for the first part, it focused on the diffraction aperture theory, especially the difference between the Fraunhofer and the Fresnel regions. Both of these approximations simplify a complicated integral in solving for the diffraction pattern in different ways, resulting in different patterns. So Fraunhofer can be observed at large distances, and the Fresnel pattern can be observed up close. And the Fraunhofer pattern is the Fourier transform of light through the aperture.
So this is a setup. We got a laser beam, we got the lenses to converge, and we got a photodetector that was attached to a computer to be able to observe the image. So this is the first one. That's like one aperture. That's in the Fresnel region, or the picture on the top of the on the Fresnel region. The one on the bottom of the Fraunhofer region. So this is for the first aperture. This is for the two slits experiment: 0.2 millimeter, 0.3 millimeters, 0.45 millimeters. That's this picture.
And then this is the square aperture, and then the pattern, the triangle aperture, and the pattern, and then the circular aperture and the pattern. So for the circular aperture pattern, it produced an Airy disk. So we used the provided MATLAB script to compare it to the theoretical Airy disk. As you can see, the experimental data is the blue and orange, while the theoretical is the purple and lighter orange here. And on both the X and the Y axes, our values were very close to the theoretical, suggesting that we had good data.
So the Airy pattern match what we have the variable for X and Y direction. Aperture can be produce different patterns at different distances between them and the detector.
So as a laser travels, its beam naturally diverges a certain amount. And by using a detector to measure spot size at different distances from the beam, we can find the divergence formula.
So that was a setup. So we got the laser, and here we got the software that can measure the beam waste and stuff like that.
And it's hooked up to the sensor right here. You just adjust the laser to get the reticle in the center of the crosshairs and measure the X and Y. So this was our data for the X and Y. I first graphed them, making sure both axes were in micrometers, and then mapped a quadratic to them using Excel to find the A, B, and C. Then, using a calculator, I plugged in each of the values into the given formulas in lab and produced these following answers, every one of which is in micrometers, except for the last two, or this one, which is in degrees. So by squaring the divergence formula, we can map it to a quadratic formula that is in terms of z to help find the coefficients. And then we can express beam waste and ZR among other values in terms of these coefficients.